co, to może zaczniemy. All right, so in this segment, we're going to discuss different models of text or language, and we're going to focus mostly on classic models, that is the grammar-based models. We talked before about sort of words and probabilities and how they can be used to do some interesting things with words and derive some interesting applications. The combination of these two gives us probabilistic grammars, so we're going to see how these are represented, and then at the end of this talk we will have some idea about what Watson does to model text. So we're going to discuss some elements of the architecture and some elements of text processing in Watson. So the simplest model, yes, is text is just a collection of words. So we have a tall, balding man is crossing a tall bridge. If these words were in a different order, it would be still the same representation. So we could have all of them in alphabetic order, which would be balding, bridge, crossing, tall, tall, after we remove the stop words. A is A, all right? And get rid of the period by tokenization. So after stop word removal and, after tokenization, where we remove punctuation marks and tokenize on blank spaces, on white space, we essentially can put these words in alphabetic order, and that would be sort of the simplest representation of this particular text, all right? So you can do many things with it. So for instance, the Lifshitz study didn't care about the order, but for instance, in the next study where we talked about diagnosis of mental illness, the word order was important. So tall bridge and bridge tall are not the same concepts, yes? This is essentially a bridge. This is the money you pay. So the concepts behind it are different. This is the physical structure. This is the amount that you pay. So order matters, all right? And so this next simplest model would be just to have the order from left to right. So if this was the only thing that was needed, then there would be no sort of ambiguity in these sentences. So if you have a sentence, include children when baking cookies, yes? I don't know if you find it funny, but in English it has two meanings, one of which is quite funny, which means that, when you baking cookies, you can add the children to the batter and bake the children together with the rest of the batter, yes, to make a cookie. Of course, it doesn't make any sense. Nevertheless, the language permits this kind of reading. So here you have another headline: miners refuse to work after death. All right. Obviously, nobody can do any work after the person dies, yes. But the meaning of it is somewhat ambiguous, because it probably means that somebody else died and some other miners refused to work. So the person who died and this collection of miners is disjoint, even though the language permits the reading that they are not. So similarly, we can have, okay, so we have this sentence and we have these sentences, okay? Residents can drop off trees, which the intended interpretation is that, after Christmas, you can drop your dead Christmas tree at some spot, and and the town will pick it up. But another meaning is that that you hang on a tree and you drop off the tree, and you are the resident that's falling off the tree. Drunk gets 9 years in a violent case or in violent case. So, well, what is the meaning of the case here? All right, is this sort of some kind of a legal meaning, or is it the container for a violence? So we have this kind of a semantic meanings. So there are quite a few of headlines like this. We will sort of use them to explore the reasons for this multiple funny meanings of the sentences. All right, so linguists like these kind of sentences because that allow them to clarify and account for certain distinctions. And if we can build a grammar that approximates human judgment, perhaps we can make this grammar programmable and create sort of a better model for a machine to understand human language. We are not there yet, but by codifying these kind of distinctions, we might be getting closer. All right. So we started with words, then we added the word order, then we had some other stuff there, such as how the things are arranged and what the meaning was. But in general, the dominating model for looking at language is this, that we have on the highest level, we have all our data, the corpus, the books that come with NLTK could be an example of such corpus. And there what we do is we prepare it. That is, we make sure that, all of them are represented in the same encoding, for instance, UTF-8. We can analyze, so find how many times, say, the word monstrous appear in Moby Dick. We can do various kinds of counts. So this would be the operations on the corpus. We can take a smaller chunk of a corpus, a document, and within we can take a paragraph of text, and then we can find the grammatical structure. We can try to account for the meaning of this paragraph. So this is, this is the next level of analysis. And then if we go a little bit deeper, well, we have words. So how do we find words? What we do is we tokenize. Yes, we find the empty spaces between words, and we say the word consists of the characters between the empty spaces, or from the characters from the beginning of the line to the first empty space. Once we have words, we can say, okay, is this word a noun, or is it a verb, or is it an adjective? So we can put some tags on these words, and that's where part of speech tagging comes to play. So this is just looking at, at words at different resolutions, but then there is some other aspects which we mentioned before, that is discourse and dialogue. This is what we have to deal with when we build a computer that can take airline reservation or engage in a chat trying to pass the Turing test. So in this case, the model must take into account something like a state of the conversation. That is, have I already given the machine my credit card number? Is the route completely specified? That is, is it a single trip, or is it a round trip? Is the hour set? Is the flight number set? All of that stuff comes into the state management. So what should be the state? What are the variables in the state? And how do we fill the values of these variables? That comes under the state management. And then, you can also look at the sound, but that comes mostly at, when you build a speech recognizer. All right, so the same view on the highest level, you can say that, you know, we have communication, okay, where we manage the task. We have corpus, where we have the data and we analyze. We have paragraphs of text, where we parse, we find meanings in these paragraphs, and we are interested in the grammaticality or truth or relations. And then at the word level, we have part of speech, assignments, and you know, tokenization, lemmatization, stemming, all these kinds of operations on the words. All right, so to understand something, we need to parse. Parsing is an operation of assigning a structure to a string. So we have a string, John hits the ball, or John hit the ball, and we want to assign a structure to it. So most grammars would assign the structure that you see here. So the ball is a noun phrase consisting of a determiner and a noun. Hit is a verb. Altogether, these guys form a verb phrase. This is the object, all right? John is a noun phrase and a subject. Subject plus a verb phrase creates a sentence. So this would be a grammar rule saying sentence consists of a noun phrase followed by a verb phrase. If we have this kind of representation, we can then create a logical representation by taking a verb and converting a verb into a predicate, okay? So the logical representation of it would be hit John ball. So we take the head noun and the head noun here. The subject becomes the first argument, the object becomes the second argument. Once you have logic, you can actually automate some amount of reasoning. So the original hope was of linguists was that by doing the conversion from a grammatical representation to logic, we will be able to, and then automating the logical reasoning, we should be able to create computers that think. In practice, it didn't work out that well because it turns out that there are many different representations, and finding a canonical representation like this works nicely for simple sentences, but it doesn't work so well for, you know, for the sentences that, for instance, appear in newspapers. So, so as a program, that program failed. Nevertheless, it turns out that being able to assign the structure, being able to at least partially create this kind of semantic representation is very useful. And it's being used in machine translation, for instance. It was used in Watson. It is used in semantic search. So the stuff is good. It just didn't go as far as the linguists had hoped for. All right. So to do that, yes, to assign this kind of structure to a string, John hit the ball, what do we need? Well, we need a dictionary that would tell us that Z is a determiner, that ball can be a noun, that hit can be a verb, but it could also be a noun, like a hit, you know, that like a music hit. So, so we need a dictionary, and John could be either in dictionary or could be out of dictionary, yes? So some words will be in the dictionary. The words that are not in dictionary as a default are assigned to be nouns. So we have a dictionary. We also need a collection of rules, all right? We have to know that to get a sentence from which we then can derive a predicate, we need a verb phrase, or another rule could be sentence consists of a noun phrase, verb, and then another noun phrase. I mean, there is more than one way of building a grammar. So we need a collection of rules. Usually, we also need a collection of examples because most current grammars are derived by a combination of, of a core that's built by linguists and then statistical rules which are created by machines. So this would be the one use of examples, just to create a grammar. The other use is that any large grammar will require a collection of examples to see if after a change the examples that were previously accounted for still works. Very often you introduce a change and things don't work as well as they did. So we need all of that. And then for most languages, we also need stuff like morphological analyzers and chunkers and tokenizers, all that kind of stuff. So why do we need morphological analyzers? Because we want to account for plural and singular, yes? We want to account for post and prefixes. So we have to account, that hits and hit would be represented by the same predicate. All right, so this is parsing. So essentially the key idea here is that we assign the structure to a sentence, to a string of words. And to do so, we need a dictionary and collection of rules, and preferably a collection of examples that can be used to test or derive additional rules. Sentences are ambiguous, okay? So we have the sentence, time flies like an arrow, okay? And it has the same structure as fruit flies, okay, which is a noun, yes, fruit flies. These are the little creatures that appear in summer on your fruit. And fruit flies like a banana, all right? So this sentence can be analyzed in many possible ways. So it could be a verb, all right? So in this case, we have time flies, the same thing as we had fruit flies, and like becomes a verb. So fruit flies are fond of a bananas, and time flies might also be fond of a banana, all right? Fly can be a verb, so airplanes fly like birds, time flies like an arrow, and there are multiple meanings of this fly, of course. Time could be a verb, so time your new programs like you timed the old ones, so in this case it's an imperative. Time the flies like you timed an arrow, and probably a few others. There are semantic ambiguities, okay? So fruit flies like a speck of sugar, all right? And is it the question that each of them likes the same speck of sugar or different? Time could be the reference to a Time magazine. It could be a comparison, and so on and so forth. So given all these ambiguities, yes, the solution is to provide multiple parses and then use rules or statistical data to solve these ambiguities and assign the most probable parse. Typically, I mean, this is, okay, you can think of it as a bizarre sentence, but if you take any sentence, you can probably find at least a couple of dozen of reasonable parses, so at least machine will find them, and after you think about it, you can say, well, that was actually a reasonable reading of it. So there is no general solution of this problem. I mean, the problem appears, and the only way to do it is you can limit the impact of the problem by using the most likely parse. Watson uses the English slot grammar, okay, so this is a traditional grammar built by a human using a large collection of examples. The parses are, instead of, top down, are created sideways, okay. So here we have an example of a parse. The sentence is she sing a song of sixpence. All right, and essentially what it does, it assigns a collection of features. So she is a noun, it's a nominative, a feminine, human, and personal pronoun. Sing is a verb in the past, singular, and it's a subject verb. This is an expression, all right, so it's a chunk that is a proper noun. A is a determiner and a singular, all right, and then we have the decomposition of this particular chunk into a song of sixpence, okay. So it gives you very detailed structure of the sentence, provides this shallow and deep structure. It also gives you the capability to do the partial parsing, and as you can see from this chunk, it can do some elements of named entity recognition. What is interesting is that even though modern parsers are mostly built by a combination of human created rules and statistics, this parser actually has better performance on various test sets, be it Jeopardy or additional or Wikipedia, than sort of the dominating statistical parser. It's been in development by Michael McCord for about 30 years right now. And let's see. And I mean, it was the basis for, for analyzing text in the Watson project. So anyway, parsing is useful. Without it, I don't think we would have Watson. But, what we need to remember from that is that, that it's about assigning the structure. So we have additional funny sentences, all right. Stolen painting found by tree, all right. So of course there is a double meaning here, that that it was the tree was doing the finding versus this was a location of the finding. All right, the red tape holds a new bridge. I mean, so there are quite a few such ambiguities, and some account for these ambiguities can come from different parsing. All right, so we have residents can drop off trees. All right, so we have here dropping off is a verb. All right, meaning you can leave your tree somewhere. And here we have residents can drop off trees, so fall off trees, the same way as cats can jump on trees. All right? So there are multiple meanings. You may want to draw some of these parsed trees, and also note that can doesn't have to be sort of the auxiliary verb here. It can also be a noun. So you could also have a reading, the residents can, all right, sort of, which of course is not very sensible. Nevertheless, the language permits it. All right. So how is parsing done? All right. So we talked about it a little bit with the example, but essentially, we have, in a typical parser, we have some probabilities assigned to various phrases. So with probability 0.7, verb phrase decomposes into verb and noun phrase. With probability 0.3, verb phrase decomposes into verb and two noun phrases. Noun phrase usually have a determiner, so the probability is 0.8. But sometimes it can be just a single noun. So these are the phrase rules. We also have lexical rules. so noun, these words with probability 95% are noun, but some of them, and these words are with 99% probability verbs, okay? Determiner is almost always, D is almost always a determiner, A is also almost always a determiner. But sometimes A can, like in a letter A, can be a noun. Well, to do a parse, you essentially see if something like this is admitted first by the lexical rule and then by the grammar rule. So for instance, if we see the word, the phrase dug the ball, well, let's see, ball is what? Ball is a noun, Z is a determiner, so do we have a rule that says determiner noun? Yes, we have it with 0.8%. So we managed to account for this. Is duck a noun or a verb? Well, duck here in this case is a noun. Do we have a rule that we can have a noun phrase or a noun consisting of N and NP? The answer is no, is not. So this dug the ball is not grammatical according to this particular grammar. On the other hand, bake AA, all right, let's see what we can have here. Determiner, noun, okay, gives us AA as a noun phrase, and bake is a verb, so we can have verb followed by a noun phrase. So despite this looking somewhat suspicious, bake AA is a perfectly good phrase in this grammar, all right? So that's, you know, that's although not very probable one. All right, so that's essentially how the grammar and parsing works on the algorithmic level. It's also a very simple model. Usually grammars are much more complex than that. Well, so the chart says here, look also at chart parsing, unification, dependency, grammar, and parsing. We're not going to cover that, although these are very important topics when building a parser. So how do we get a grammar? We mentioned some of it before. Manual writing of rules and automated testing. So this is how English thought grammar was created. Manual annotation of text and automated derivation. This is sort of the dominating statistical model. There are some experiments in inducing grammars from text without any annotations, but it's too early to tell whether this is going to be successful. So in any case, I mean, I would say that this is some combination of manual annotation or manual writing with statistics seems to be the most promising approach right now, despite the fact that ESG seems to be the best grammar currently in production. All right, so this is the grammar. Grammars achieve sort of syntactic parsing accuracy of about 90%, but we can do better than that if we only care about part of speech, that is finding nouns, finding verbs, finding prepositions, all right? So we can get close to 97% if we're going to do so-called part of speech tagging, and very often this is enough for certain tasks such as named entity identification. A simple method, okay, of assigning the most common tag for each known word and a proper noun to all unknown words gives you 90% accuracy, okay? So a very simple rule can give can give you very, very high accuracy. So the game is really played between 90 and 97%. There is no challenge in this case to get to 90%. On the other hand, getting a grammar that has 90% accuracy in parsing is very challenging. Doing the same for machine translation is even more challenging. Being able to do correct inference from text more than 60% of the time is extremely challenging. So some tasks are easier, but the more meaning is involved, the more difficult the tasks become. All right, so another concept that is used in computational linguistics and in language processing is the principle of compositionality. That is that the meaning of complex expression is determined by the structure and the meanings of the constituents, all right? So what it means is that if we want to account for the different meanings of these three sentences, yes, we do not have to go beyond these sentences as long as we understand English. So if we know what blind means, what a Venetian means, what a window means, and what to open means, then essentially the meaning of it can be obtained by parsing the sentence and then assigning, meaning of the constituents. So in this case, open would be the main predicate, man or a blind Venetian man would be the subject, and the window would be the object. This has similar words, all right? So open again would be the predicate, but in this case, what is being opened is not the window, but a window blind. So essentially, the shade on the window. And this is a particular type of the window blind, the Venetian window blind, and we just have a man that's opening it. So the principle of compositionality is important because it tells us that essentially if we have a good dictionary and a good parser, then from that we should be able to derive the meaning of every sentence. Indeed, that seems to work in the situation when the parser works and the meaning of the words is in the dictionary. It is not just of practical interest, but it's of theoretical interest, but it's also practical. All right, transfer $100 from checking to savings has a different meaning than transfer $100 from savings to checking. Nevertheless, if we understand the concepts, yes, we should be able to derive these two meanings. Just from the meanings of the part and the way these words were arranged. So without compositionality, we would have to enumerate all possible ways of accomplishing a transaction, all right? So in this case, at some point, I was working on a system that would permit banking by phone using speech. We built such a system for one of the banks, and only for transferring $100 from savings to checking, you were able to do this simple transaction in more than 10,000 different ways. All right, so this is a very simple concept, move $100 from checking to savings. Nevertheless, there was 10,000 ways of accomplishing these transactions. So having it all enumerated and then, you know, sort of mapping these 10,000 strings into different ways of expressing it by phonemes, yes, because the speech recognition was also involved, would be just very, very time consuming. But because of compositionality, we don't have to do it. We just have to have the concept of the checking account or checking, the concept of transfer, map, transfer into some operation, map checking into the particular account number, savings into a different account number, and that's the only thing that's required to understand these sentences. So it's a very important principle. Also, as you see at the bottom of the slides, programming languages are compositional, right? So if you have an operation, you know, if you have, you know, equals plus, x equals plus y, well, basically the order of the symbols determines the meaning of this particular operation. Logic is also compositional, so actually the inspiration for compositionality in computational linguistics comes from logic. All right, so syntactic meaning is derived from syntactic form, and you can see this. Okay, so here's another parse. So every patient respects some doctor. All right, the parse is the link grammar parser, and we have a link there on the right of the slide, so feel free to experiment with it. And again, because of the principle of compositionality, we're going to have similar logical representation of similar syntactic patterns. So every patient respects some doctor, and every old patient respects some doctor, have similar representations. So here we have the additional predicate old, yes? And these are the quantifiers for every X, which is every patient. There exists a doctor such that the patient respects the doctor. Are you familiar with quantifiers? Did you have logic? Yes, okay, so all right, so in any case, what you see here is another application of the compositionality principle, and another a way of representing the structure of the sentence. So this is the link grammar from the people at Carnegie Mellon University. All right, so your homework is to check the link grammar, play with it, get some intuition, and read about semantics at the Stanford Encyclopedia of Philosophy. So the final concept is pragmatics, which studies the ways in which context contributes to meaning. So let's look at some examples. So this is where, you know, yes, we can get from the grammatical structure, we can get some basic semantic structure, but what it really means is not that obvious. So for instance, the sentence, "you have a green light," is ambiguous. It could mean that "you have a green light" means that, for instance, this light is not white or green. Yes, if this light was green, somebody here in the audience could say, "you have a green light." Yes. It also means the usual. Yes, you have a green light when driving your car. Okay. Metaphorically, it means you can go ahead with the project, you can continue with the project. But going back to the first sentence, yes, if there is a green ambient lighting, my body could have a green glow, and that would be another meaning. You know, somebody saying you have a green light, your body glows green. All right, it could also mean that you have a light bulb. So all of these are different, deeper meanings of "you have a green light," even though maybe we would represent it, you know, sort of as a predicate, "have you green light." So that's why we need pragmatics to really know what it is about and what action can be taken based on on the semantic meaning. Now notice that in the case of transferring $100 from checking to savings, the pragmatics is sort of vacuous. Yes, it's incorporated in the program. We don't have to worry about it. We don't have to compute it. It's obvious what the transfer means. And that's usually the case with technical human-built systems, that pragmatics is trivial and it's built in. So final thing, let's talk about the meaning representation in Watson. But for that, we need to talk about Watson architecture, evaluating evidence, and deferred type evaluation. So this is what Watson does, yes? I mean, we saw this slide an hour ago or so. We have a question. After analysis, a search is performed. Then Watson retrieves evidence that for each candidate, Watson retrieves evidence which might or might not support this candidate as an answer to this question. All right? And this evidence is scored, and the highest scoring candidate answer becomes the answer to the question. Some probability is assigned. So this is, you know, this process of assigning pieces of evidence and then scoring these pieces of evidence and, you know, combination, assignment, final score, relatively computationally intensive. So what happens there is that we have dozens of scorers which generate numbers, okay? So numbers that are assigned to pieces of evidence associated with candidate answers. So once we have these scores, we generate a composite score for each candidate answer, and the highest scored candidate answer wins. So notice that here, sort of, there is no talk yet about parsing or anything like that. There is an architecture which supports the production of certain numbers. So this is a different, somewhat different view than what we have seen so far. We do not necessarily count things. We do not necessarily assign grammatical structure. If such structure is assigned, it becomes just part of a general picture, but not something that gives you the final answer. So let's look how this is done. So for instance, we have a question. In 1894, C.W. Post created his warm cereal drink Postum in this Michigan city. All right, so the question is, which Michigan city satisfies this predicate that in 1894 Post created the warm cereal drink Postum? All right, so the lexical answer type, the thing that we are looking for, is Michigan city. We can, from parsing, okay, we can derive that we have a date and we have the relation create, post, and cereal drink, and we have a bunch of keywords that could be also used for search. All right, so that's what we get from question analysis. So now the search, we're gonna be searching for 1894 C.W. Post created, but we are not searching for Michigan city because, you know, that's the answer we are looking for. So it won't be stated as Michigan city. It could be stated as Detroit or Ann Arbor or something else like that. So here is what we get from the search. From the search, we get a bunch of documents, and the titles of these documents are General Foods, 1895, Post Foods, Battle Creek, Grand Rapids, and a bunch of others. All right? So these are the candidate answers. The titles of documents are treated as candidate answers. What's happening next is that we take each of these, so General Foods, and we add it to the previous query. So we now have a query 1894 C.W. Post created and then General Foods, yes? Or Postum and then General Foods. Then we add 1895, and that's a separate query. Battle Creek would be a separate query. Grand Rapids would be, together with these words, would be a separate query. So what do we get? Well, we get more documents. So that is our evidence. We retrieve it by search. We're going to be talking about search tomorrow. So we're going to see how these things are retrieved and what happens with these pieces of evidence. So now, all this machinery that we discussed so far can be used to assign numbers. So we can see if there is a relation create, post, and serial drink somewhere in this document, all right? If it is, we're gonna put, some number there, say 6.3. That would be somewhere here, say in this column. We can see if there is taxonomic relation, that is this a city? So is General Food a city? Is 1895 a city? Is Battle Creek a city? Is Grand Rapids a city? Okay, so we can ask this kind of information and assign and put some numbers there. And then is there a temporal relation? So is there a date or similar date mentioned in the document? And that would be in this column. So essentially we get a bunch of numbers. So we use parsing to find some of these relations and then score how close relations in the document approximate the relation in the query. We get a bunch of numbers, and then we combine these numbers together using a formula called logistic regression, and we get that Battle Creek, which is a city in Michigan, has an 85% chance of being correct, and indeed it is a correct answer. So again, I think that we're going to be talking about how to do this combination using logistic regression tomorrow. So what's happening there, okay? What's happening in Watson, and this is one of the big Watson innovations, we call deferred type evaluation. Since in general, meaning representation is an unsolved problem. Yes, we can go from a parse tree to some kind of a logical representation, but as you saw in this example with the green light, it doesn't give you complete meaning. So what Watson does is it lets many scorers focus on different aspects of meaning to show the degree of match between the candidate and the relations in questions. Okay, so the documents about the candidate and the relations in questions, we can score to what extent they match. So in a sense, what we are saying here, that passages have no meanings, they only provide candidate scores. So we measure some aspects of meanings, but we never really have a complete meaning representation that would account for, semantics and pragmatics. So this chart simply summarizes this idea that yes, there is syntax, semantics, and pragmatics in Watson. It is used to create the representations, but these representations are often faulty and they are almost always incomplete. So therefore, instead of looking for a perfect representation, Watson attempts to do deferred type evaluation. If we know what the question is, we're going to see to what extent candidate answers match the relations in questions, and this can be done by a collection of measurements and not as a canonical way for representing meaning. So that is a departure from both traditional logical approaches to meaning and from the statistical approaches to meaning. It combines both of them in a very novel way. All right, so what are the concepts that we mentioned in this lecture? So we talked about words, we talked about syntax, we talked about semantics and pragmatics, and we talked about deferred type evaluation in Watson, so this should be fresh in your memory. Words, what is important here is to understand that finding words is not necessarily a trivial process, especially in languages like Chinese or Japanese where there are no spaces. But even with languages where we have spaces like English or Polish, finding the canonical representation of words is non-trivial because you have to account for plural, singular, for cases, tenses, and stuff like that. All right, so the simplest way to find this canonical representation is to tokenize on empty spaces, all right, on white space characters, and then do lemmatization or stemming. So lemmatization uses a dictionary, and stemming basically chops off the final S to, you know, in the plural. Okay, I mean, the rules are somewhat more complicated, but the idea is that if you have the word words, the stem would be just word, because S followed by a blank space or S followed by the end of a token should be dropped. Syntax, what you need to remember from that is, well, it's basically assigning structure to a sentence, and you do it by having rules for doing so. Yes, that is a grammar rule that says sentence consists of a noun phrase and a verb phrase, and then somewhere there you have also a lexical rule which says that a duck is a noun and bake is a verb. All right, so that's what you need to remember about syntax. Semantics is a mapping of syntax into some kind of a logical form. It doesn't give you a complete representation of meaning, but in some cases, such as when you do airline reservation or transfer money, it's enough to to produce a desired result, to engage in dialogue, to perform an action. A deeper meaning is often given by pragmatics. We saw it in the green light example, which can have many different readings. And deferred type evaluation sort of avoids the problem of building a perfect semantic or pragmatic representation. We talked about different levels of modeling text, such as corpus, document, paragraph, sentence, word, different features, words, order, syntax, semantics, and pragmatics. And we also talked about different types of models, that is statistical, logical, mixed, and so-called deferred type evaluation in Watson. So this is the end of this particular lecture, and let's do a 10-minute break. Zainteresowany właśnie przetwarzaniem tekstów, to chyba będą też jakieś możliwości. Także zobaczymy. Tu się muszę podowiadywać, co się dzieje. Dobrze, to co, to zacznijmy? Dobrze.
Grupy 401, 402.
Dobrze, to ja to po prostu dam, ktokolwiek chce to wziąć. No ja nie wiem, czy to ma mieć wpływ na końcową ocenę, czy nie, to nikt mi na razie nie powiedział, więc jak mi powiedzą, to się zastosuje. Proszę? Największy wpływ. Największy wpływ? No nie, egzamin powinien być największy wpływ. Tak naprawdę projekt powinien mieć największy wpływ, no ale projektów nie mamy czasu robić niestety. Dobrze, to w takim razie możemy to przełączyć. All right. So let's start. All right, so after all this general introduction, hand waving, and so on and so forth, we have the basic concepts in our heads. That is, we know and remember the Bayes theorem, and we're gonna review it in a second. Also, we have talked about parsing, tokenization, semantics, stemming, lemmatization, all this kind of stuff, yes? So we know that there are different levels of processing, some higher level, some lower level, and we will start applying it, okay? We will start applying these concepts to predictive analytics. So one example of predictive analytics is classification or categorization. That is, we want to decide whether some document is in a given class. So is this document about sports? All right, that would be an example of classification. Maybe we would like to do more, put a document in different categories. So this document is about sports and politics, or about sports and money. So we're gonna put the document into these two categories. But typically, I mean, these words are synonyms, and they essentially mean we want to make a decision whether a document is about something. So earnings, sports, politics. The simplest way to classify is to use a Bayesian classifier. So we're gonna go into details about how this kind of classification is created. It's a very neat concept. It uses the Bayes theorem as expected. It's not a particularly difficult concept, but once you understand it, you will have the basis for, for understanding a lot of predictive analytics. I would say that there are two major concepts in predictive analytics that you should understand, and I will definitely cover sort of Bayesian classification, which is the first one. The second one would be expectation maximization, and I'm not sure how much time I'm going to have to cover it, but both have to do with, are widely used in machine learning, and they are used in dealing with text. So a general concept, we're gonna see some demos, or at least, I have the demos and they are somewhat visible on the screen, but they're gonna be available for you to view offline. We're gonna see some application of classification to credit card fraud detection. And then we also will cover some other types of classifications, such as nearest neighbor classification and rule-based or decision tree classification. So altogether, I would say that Bayesian, nearest neighbor, and decision tree is the core of classification algorithms, and they appear in different variants in many different places. Let's go to the next slide, if we can. All right. So in categorization, we have a collection of new documents, all right? And we want to apply labels to these documents. Essentially, we want to put these documents into buckets, all right? In addition, we would like to know how likely it is that the document should go into a red bucket versus blue bucket, all right? So that's the input. And the buckets and probabilities are the output. Our resources are training corpus and test corpus, okay? So training corpus is a collection of documents where the labels have been previously assigned. And the test corpus is a collection of documents that we also have assigned labels, and we use it because we want to know how good our classifier is, all right? So That's the arrangement. And how do we go about it? We use a collection of training documents to learn a classifier, all right? Then we use a collection of test documents to choose the best classifier or to determine how good the classifier is. And then finally, we can apply the classifier to new documents, and because of this testing done here, we can actually have some intuition about how well this classification works. In general, if you apply a classifier to a completely different collection of documents, you have no idea how well it's going to work. So it's important that the training documents, test documents, and new documents are all coming from a similar collection. So for instance, this could be newswire articles or abstract of new medical discoveries, yes? So you don't want to apply sort of the stuff, the classifier that you learned for news articles to the abstracts of medical discoveries, because the categories won't make sense, the vocabulary is different, and your classifier is unlikely to work. All right, so how do we go about finding a classifier? First of all, we need to prepare documents, all right? So what it typically means is that we have to decide how we're going to represent a document, okay? We're going to see that in an example in a second, but essentially what we want to do is to say, okay, here's the beginning of the document, here's the end of the document. Here's the category of the document, here is the text document, okay, of the document. So we need these things. We have to say, all right, this is, the machine has to know where the document ends and where the document begins, yes? And the machine has to know where the text of the document is. And since we have training corpus and test corpus, for these two, we have to have the label saying this is the earning category, this is a sport category, this is, some other category. So usually this representation is XML, a representation, and a particular format that is very often used is called the track representation, which looks as follows. You have a doc tag at the beginning, end of doc at the end. You have the title of the document. You have the number of the document. You have the text of the document. That's the minimum representation. All right. So once the documents are prepared, you want to create a dictionary to limit the number of features. So here is where, this stemming lemmatization is important, all right? You want to know that if the document is about sports, yes, that game and games are essentially the same token, yes? Because winning games and winning a game, it would be the same concept, or win a game and winning the game, yes? So what you want to do, you want to create one representation for win and winning, game and games. So you can do it by stemming in English or by lemmatization, which is essentially going to a dictionary and seeing what is the base form of the word. So first you limit the number of, first you do this lemmatization and stemming, and then you put a limit on the number of words. Why do you want to do that? Because otherwise your classifier will have too many features. It will be less computationally efficient, but even worse, it's going to represent your training collection too well. It will be incapable of generalization. So therefore, what you want to do, you don't want to have, say, 10,000 words in your dictionary that you're going to use for classification. You may want to have, say, 600 words. What is the right number? Well, you can experiment with it. You can sort of try different sizes of dictionary and see whether your classification accuracy improves or not. But typically what you want to do is you have to have about 10 times as many documents as you have features, or in this case, the feature is a word for Bayesian classifier. So for instance, if you have 5,000 documents, you may want to have a dictionary of about 500 words. That's, you know, a rule of thumb, but it can be experimentally tested. So you have a dictionary. That would be the first step. Since machines operate on numbers, you want to represent your documents by numbers. Therefore, we create something which is called a feature matrix or term document matrix based on the dictionary. What it means is that we take the dictionary, we take the document, and we see which words in the dictionary appear in the document. For those that appear in the document, we put ones. For those that don't appear, we put 0. For words out of dictionary, we just completely ignore them. So we have a, you know, that means that each document is going to be represented as, say, 500 long 0 binary vector. So that would be one representation. We could also have a different representation. Namely, if the word, say, game appears 3 times, instead of putting just 1 because the game appeared in the document, we can put number 3 because we want to put the frequency of the document. So there are variants of this theme, but essentially we convert the document into a collection of numbers. And since we do it for many documents, we call it a feature matrix, and each row of the matrix is one document, it's a vector. Then usually what we do, we experiment with a number of algorithms, and we can set some parameters of the algorithm. We want to see what works. Some algorithms work better on different data, and we're going to see some examples of it. And well, if we find the algorithm that works, we usually apply it in practice. Here in the note, I'm saying it's still more art than science. There are no ways of really figuring out what's going to work best with a different text corpus. All right, basically you have to experiment. That's why some of these tools that allow you to do experimentation, you know, in bulk are so useful. So, for instance, Weka, which comes with a way of experimenting with different classifiers and different parameters, is a very useful tool. You create a certain matrix representation called the R format for Weka. You then go to the tool and you can experiment with different collection of parameters, see what works. And sometimes it's the Bayesian classifier, sometimes it's the rule-based classifier, sometimes it's some, you know, more exotic classifiers, such as, you know, a collection of trees. All right, so that's how we go about it. And we're going to go through some of these in details. So let's look at the naive Bayes classifier. All right, so we're going to start with the Bayes theorem. All right, so this is essentially a restatement of the Bayes theorem, except that saying A and B, we have a label. Okay, so a label would be sport, and the document would be, you know, the vector representation of the document. So the probability that a given document should be assigned a label such as sport, okay, instead of label, sometimes we use class or tag, is what? Probability. Okay, I mean, maybe we should just go back to the Bayes theorem. Okay, if we take this guy, probability of the document, and multiply it here, yes, we're going to get essentially the statement of the conditional probability of label and doc. All right, so this is the statement of the Bayes theorem, that if we have a document that we are looking for a label, we can first know what is the probability that of doc given label multiplied by the probability of the label divide the probability of the document, all right? So that is the statement of the Bayes theorem. And what do we need? Well, we need some of these values on the right, yes? We need to know probability of the label, probability of the document given label, so this guy here, and we need the probability of the document. All right? So how do we go about it? Well, it's not obvious what they are, so let's just analyze this situation. Again, that's the statement, all right? We are looking first of the probability of the label, which is the easiest. That is, we are asking the question, what are the chances that a randomly chosen document will have the tag L, okay? This is our label. Well, since we don't know anything else, we can just say, okay, well, we have the data, we have the training corpus, so we can simply ask, how many documents are labeled sports, all right? So if we have 5,000 documents and 500 of them are labeled sport, what is the probability of sport as a label? 10%. Yes, 10%, exactly. So this is easy, yes? Using your training corpus, you find out how many documents are labeled earnings, how many documents we have in your training corpus, divide, and this is the probability of the label. So we are done with this part. So let's look at the other guys. All right, so this we have here. All right, so here we have the figure that we care about. All right, so if we have, all right, so here's the illustration. If we have documents that have words, this is our dictionary, 4 words, W1, W2, W3, W4, all right? This is going to be on the test, by the way, on the exam. That is, we're going to have something similar, all right, a table. So this is our matrix representation of documents. So this document has the word 1 and the word 4 and is assigned label 1. This document has only word 4 from the dictionary and has a label 0. This one has first, second, and fourth word and also has a label 0. So, and the final one has 1, 2, 3. First 3 words, doesn't have the fourth word, and also have a label 0. So if we look at this formula, number of docs labeled L to the number of docs, well, so probability of label 1, how many times do we have 1? 1, 2, 3, 4 out of 10. So this is 40%. Probability of label being 0 is 60%. Notice that these probabilities add to 1 because we have only 2 labels here. Okay, it's a binary classification. All right. All right, so, okay, so again, this is the term document matrix also with the label. When we have new data, we don't have the label. Yes, we will have to predict this label based on what we learned from this training data. So that's going to be our task. All right, so let's continue. So let's look at probabilities of words. All right. So we are looking at probability of word given label 1, okay? Because, I mean, we really don't know what to do with this doc, but we can sort of compute some of these. So how representative is word 1 of label 1? Well, word 1 appears in 75% of the documents that have 1. So if we look at this guy, yes, there is word 1. If you look at this guy, there is word 1. Here we have word 1. What did I miss? Oh, here we have class 1, but this word is not present. Instead, we have word 2 here. And word 2 appears in 25%. And then this is sort of 50-50 here. So, okay, so, well, we can ask the question. Okay, before in the slide we had that the probability of label being 0 and or label being 1, they have to add to 1, but is this true, for instance, that the probability of word appearing in label 1 versus word appearing in the document labeled 0, that these probabilities have to add to 1? Well, the answer is no. So the simplest example would be words like stop words which appear in any document. Yes, so in the document about sports, you're gonna have words like where, which, to, the. Okay, and in the words in the documents which are not about sports, you're gonna have the same words. All right, so despite the fact that, you know, we have two different labels, I mean, the probabilities, you know, the probability could be actually bigger than 1 here. So this is not true, all right? It would be nice if we had something like complementing probabilities, because, say, if something appeared in L1, it wouldn't appear in L0, okay, then this would be the best situation. But sometimes, but there is really no, I mean, how to say, there is no use of trying to find something like this for classification, all right? So the next question is, why do we care about these probabilities? Well, we care about these probabilities because we are interested in estimating these two guys. And the only way to estimate probabilities of document given label and probabilities of doc is to know something about words in the documents, yes, because that's what the documents consist of. They consist of words. And the only instrument that we have is counting. So counting and, you know, division, that's what we're gonna use here. All right, so let's look about how we're gonna use it. All right, so this slide answers this question. The sum of probabilities for all labels is 1, but there is no obvious relationship between probabilities of individual words. And the naive Bayes method relies on using collection of words to distinguish between classes. So it's not just a particular word that's going to be there when talking about sports, but it's going to be, you know, winning a game versus, you know, playing a game on a computer, or, you know, winning something, you know, playing cards, yes? So you're going to have a combination of words, collection of words, that's going to give you information about the class. All right, so let's see. Okay, so here are some probabilities, some distributions. So for instance, we have that, you know, we saw this on the previous slide. This is the same thing, the same table for the label 0. So we see the W1 appears in 50% of documents with label 0, W2 appears in 67, W3 appears in 33, and W4 appears in 55. So what we see here is that, you know, if we look at it, if we look just at these numbers, they do not tell us much. However, if we look at some combinations of these numbers, maybe we can get something out of it. All right. So the naive Bayes classification, okay, the word naive comes from the fact that we assume that language is like playing dice or playing cards. That is, when you toss a die, yes, probability of having 2 and 3 in 2 tosses is the same as the product of probabilities, okay? So if you want to get 2 and 3, you basically multiply probability of having 2, which is 1/6, and probability of having 3, which is 1/6, and that's what you're gonna get to get the collection 2, 3, all right? If you want it as a set, then you have to add probability of 3 in a toss times probability of 2 in a toss. And this is called the independence assumption. So essentially it says if we apply it to words, okay, so what we are going to say is the probability of 2 words being in a document is the same as the product of probabilities of the word 1 being in the document and the second word being in the document. So this is the crucial moment, okay? We are assuming that the words are distributed independently, that really one word doesn't depend on the other word. That is obviously false, but it often works. And, you know, all models are false at some level, but we need them to, you know, to do the modeling, okay? I mean, no model is perfect. So essentially we are assuming here a very imperfect model of language, but given enough data, it turns out that this model works reasonably well. So again, what we need to remember that this is the naive part. This passage, okay, the description of probability of a bigram as the product of probabilities is the independence assumption, and that's where the word naive comes from. All right, so given that step, okay, this crucial step, now we can go back and estimate the probability of the document and the probability of the document given label. We can do it because we have the probabilities of individual words given label and the probability of individual words, you know, just in a distribution. So here we have the table of probabilities that you have seen previously, and now we can approximate the probability of a document having label 1 by probabilities of individual words based on the subset of the training set which has label 1. So what do? Well, we write this expression as we take the words which are in document, take their probabilities from this column, all right? And for words which are not in document, we take 1 minus probability of word given this column. So that essentially describes a document. What are the chances, you know, that individual words appeared? And for those that didn't appear, we also want to put it there. So that is the naive Bayes formula for estimation of the probability of the document given label. All right. So now we have this part. Okay, we had this part before. So the only thing that we care about right now is this part. But notice that usually in classification, we just want to know that the document has a label 1 or a label 0. All right? So it really doesn't depend, you know, which probability is higher, doesn't depend on this part because this part is the same. So a new document will have this probability, and the difference between label 1 and 0 is going to come from this part. All right. So let's look at an example. So we have a new document. It has words 2, 3, and 4. Should it be labeled 1 or 0? All right. This is the base formula. This is the naive base formula. All right. This is our data. This is the probability of a label. All right, so we're going to substitute these numbers. And what are we going to get? Well, we're going to get for the document D, we're going to compute it for label 0 and do the same computation for label 1. We're going to get this expression for label 0 and this expression for label 1, and maybe someone tell me which one is bigger. All right. So let's look at it. Okay, these two can be ignored, yes. These two can be ignored. Here we have 25. So it looks like this might be bigger, yes. Probability of D, even label 0, should be larger. All right, so this essentially summarizes these points. We don't need the probability of the document to decide which label is more likely. What else can be said? That probability estimate using these methods are not very reliable, but in practice, the only thing we want to know is what is more likely, okay? And in practice, what happens is, if the probability is bigger than, I don't know, 0.3%, and the probability of the label 1 is bigger than the probability of label being 0, then we assign label 1, and otherwise we do the opposite. All right, more about it later, and we're going to see how it works in a second. All right, so I'm going to show you sort of application of using naive Bayes in the toolkit called TMSK that comes with this particular book. It's a very nice book written by these two guys, Shalom Weiss and Tong Zhang, used to work with me at IBM, so I know them reasonably well. It's a good collection of text mining tools to play. So there is TMSK, and there is also a rule-based system for building rule-based classifiers. Another nice thing about it is that you can go as deep as you wish. So if you want to do a lot of mathematics, you will find a lot of mathematics in this book. If you just want to know how to use the tools, you can learn them relatively fast. The book has probably about 10 exercises per chapter. So going through these exercises is good to shape your intuition. So, it is a nice book, all right? It's not perfect, but it is a nice book. So if you are interested and have, I don't know, $55, you can get the book. All right. So before we go into the example of doing this Bayesian classification, I want to say a few words about the data that we're going to use. So this is called the Reuters 22K, or sometimes called Reuters 21K corpus. It's a corpus, I think, from the beginning of 90s. It has a collection of news articles that have been assigned categories by humans. Okay, one article can have multiple categories. It's already in XML. It's being widely used to test the quality of classifiers, and usually in a university setting. For practical settings, there are bigger collections, and usually companies that have problems create their own corpora. So what do we have there? Well, we have, we're going to be using 11,000 documents partitioned into a training set and a test set. And what else? Let's see. Okay, data format. So this is the data format. So let's talk about some elements of the format. So each document starts with the tag Reuters and ends with a tag and Reuters. It's in XML. Well, these are some additional metadata. This Reuters collection has been prepared for use as, as a training tool by a professor from MIT named Lewis, so that's why it's called Lewis Split. All right, it has a bunch of other metadata. So here, the article is from 1987. It has a topic earn, and that's going to be the topic that we are interested in. It also has a topic places USA, but we don't care about this. So you have two classes. It is not about people, and it's not about organization. It's not about exchanges. It's not about companies. All right? At least that wasn't how it was classified. So we have a body. So this is where the text is. So the text is between body and end of the body tag. And it says Champion Product Inc. said its board of directors approved a 2-for-1 split of its common shares, and so on and so forth. All right, so that is the text. So this is going to be used for classification. So as you see, for instance, here we have 2-for-1 split. Should it be one token in tokenization? If we do tokenization based on a blank space, this would be one token. If we do tokenization based on, on just caring about words which have letters and numbers, these dashes will be deleted, and this would be 3 tokens. So the tokenization will determine what can be counted as a word. Similarly, should April be treated as one token, or do we care about the date, which is April 23rd? We have some interesting expressions like 5 million is written in words, but 25 million is written as 25 MLN. All right, so anyway, so depending on data preparation, you can have a different term document matrix obtained from this particular document. Another thing that can be said about, we mentioned some of these classes, but the classes are not evenly distributed. So for instance, earning class has the largest number of documents, so has 3,000 training documents and 1,000 test documents. But for instance, the corn class here has 182 training documents and only 56 test documents. Typically for classification, you want about 40 documents per class at a minimum, okay? That's again a rule of thumb. Let's see, so this is, this distribution is from Stanford NLP. There is information retrieval book available online, so you can read it if you wish. I mean, that's the book by Chris Manning and Schutze. So let's see. All right, so this is a diagram of data set composition. This is the fact that, you know, a few classes can give you almost 95% of, or maybe not a few, but a few dozen classes give you 95% of all documents. So we can do, maybe we can do the demo, all right? So the description of the TMSK package is available freely online, so you can read about, you know, how this particular package can be used, but you need the book to access the software. The book has a code, and you have to enter the code to download the software. We're gonna go through these steps related, you know, to data preparation, which is tokenization, dictionary creation, by setting the file called properties. We're going to create a classifier, we're going to run a classifier, and let's see the result of the classification. So let's just do that. All right. We talk about that. All right, so what you're going to see in the demo is that I'm going to edit a properties file to essentially tell the machine what to look for. That is, we have to specify where the beginning of the document is and where the text of the document is and what the label is. All right, so that's what we're going to do. All right, so let's just switch to naive-based videos. All right, so all right, so this is the properties files where essentially you have to say where, you know, where the document is. So this is the tag, where the text of the document is, where the label is. Then you have to specify the training file. So the training file is in trn zip, where you want what your dictionary is going to be, whether you're going to use stop words. So for instance, you're going to delete the words like to, from, it, how you're going to vectorize, okay, so the name of the term matrix vector, and a bunch of other parameters that we're not going to go through. So the first step is essentially specification of, you know, what are the names of the files you're going to use and whether you're going to do certain things or not, such as, you know, what your stop words will be. Are you going to use a stop word dictionary or not? All right. So that is the first step. Now, if we go to the next step, all right, we're going to create a dictionary. All right, so this is really not visible, okay, but I'm going to read it. So it says, there is a command which says Java make dictionary with the number of words that you want in the dictionary and the name of the category, and then the name of the dictionary. So it's Java make dict 550 earn dict 500 dx, okay? It is almost instantaneous. And maybe the words of the dictionary will be visible once we print them. Okay, so gonna print them on the screen. Okay, so we have stuff like adjust, class, federal, lead, requirement, inventory, seek. All right, so there is a bunch of words in the dictionary, and the funny thing about it is, even though I specified that I wanted 500 words, the actual count of words in the dictionary is 443. All right, I don't know whether it's a feature or a bug, but basically what they do is they first create a dictionary and then they subtract the stop words from the dictionary. So if you want exactly 500 words, you have to have, create a bigger dictionary and cut it. The next video is about creation of term document matrix. All right, so in this case, the command is vectorize, all right, and given the parameters files, the machine knows what to do, and it creates a representation of the term document matrix. As you're gonna see, it looks a little bit weird, so let's look at that. So essentially it has, it just has not certain collection of numbers, all right, and the name of the class 0 or 1 at the beginning of the row. So that's the vector representation that is used in this particular set. Is this the same? Let me just see. Oh, okay, let's look at, no, that was fine. Let's look at this. So, here now I named my vector file earn500vec, so I need to again go back to the properties files and change the name. So now I have my vector file specified, and with that step we can generate a classifier. So we're gonna generate a naive base classifier as the next step. All right, so the command is simple and the result is almost instantaneous. So we have Java and base and then the name of the classifier, which I called NB classifier. And what you saw there was a collection of numbers, which is some collection of weights on particular words. All right, so the internal representation is not given to us, and it doesn't look exactly as in the examples that we use to explain the idea. And the final step is testing the classifier. So if we run the test, the command is test and base, and you specify the parameters. So we are getting here the number, precision 98%, recall 78%, F measure 87%. So we will explain these concepts in a second, but it essentially says that the ones that are classified and as earnings, are classified pretty well, but it doesn't get all the earnings reports. So the files, it generates two files which tell you, okay, I put this document into positive, this document into negative, and you can then examine these files to see, if some adjustment to the classification method might do a better job. So anyway, so this is just to show you that these processes, these tools work reasonably well. They work really fast, and therefore, they are amenable to applications that, for instance, require fast changing of your data sets. So naive Bayes classification is very often used in spam filtering. So you get email, most of the email is spam, most of the email sent is spam, and probably about 99% of that spam gets filtered by naive Bayes classifiers. All right, so let's go back to the lecture and talk about some of this stuff. All right, so we talked about, specifying the properties to tell the machine where the documents are and where the text of the document are and where the label is. So these are the three things that the machine must know to build a classifier. All right. We need to specify the size of the dictionary and where the dictionary is, where we are going to use stop words or not, where we're going to use stemming or not. So some additional parameters. What is the minimum frequency of words that are included in the dictionary? And after that, we are ready to do it. All right. So what you saw was preparation of a dictionary, generation of the vector, generation of the classifier, and application of the classifier. So we did that. These were the commands that we used. Make dictionary was the command to create a dictionary file. Vectorize was the command to generate vectors. Creation of classifier was Java and Bayes, and application was test and Bayes. So very, very simple steps. And these steps are applicable to any method of building a classifier. That is, we usually have to decide what dictionary we're going to use, how we're going to make vectors. After that, we create a classifier and we experiment with the classifier. So the results that we got here are precision 98%, recall 78% or 79%, rounding upwards, and F measure of about 87%. This is not optimal, and we still have to explain what these terms mean. But what you have to get out of it is that there are ways of measuring the quality of classification. So these three terms, precision, recall, and F measure, will be explained soon. But before we do that, let's compare with sort of other classifications. So for instance, okay, the best naive Bayes classification for the earning class gives you about 96%. Some other classification methods can give you less or more, all right? So 98% for decision trees and 98% for support vector machines. So we see that, that these methods, at least for this particular class, seem to work better. In general, support vector machines seem to perform better than naive Bayes, but they require more extensive training. I don't know, I don't think I have time to go deeper into that, but the bottom line is that, that for naive Bayes, by experimenting with the parameters, we could probably get it to about 95, 96%. So there is room for improvement there. All right, so now we need to discuss the measuring of performance. So we saw these terms, precision, recall, and F measure. All right, so what do we have here? All right, we have the area in the middle, all right? And green, green, and red. All right, so the red regions represent errors. On the left of the line, these are relevant documents which were not found. So these are called false negatives. On the right, we have things that have been retrieved but which are not relevant, which are false positives. Okay, so we have false negatives here and false positives here. This is the stuff that got retrieved, yes? So essentially what precision and recall measure is, so precision are quotients of the green region by respectively the oval and the left region of the diagonal, this thing. So that's the explanation of the precision and recall. So precision says, all right, if we retrieved these documents, how many of the retrieved are correct? So in this case, what will be the precision? All right, how many dots do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 dots. All right, the good stuff is here, yes? So what is the precision of our query here? It's 8 out of 12, all right? So that is our precision, sort of the quotient of the green to the oval, all right? And what is our recall? Well, these are the documents. We are interested in these dark dots, yes? So we have 8 documents here, and we have, what is it, 5, another 12 here. So we have 12 and 8, 20 documents that are relevant, but we retrieved only 8 out of 20. So what is the recall? The recall is 8 out of 20 or 40%. All right? So this is, all right, so again, the precision tells you how many good documents you have in your answer. And the recall is what is the percentage of relevant documents that you got. All right, so this is the illustration here is, is in these green and red regions. The green is good, red is bad. The documents we are interested in are in these dots. So these are the relevant documents are dark dots, the irrelevant documents are white dots, and what we compute is precision, that is how many black dots we have among all dots retrieved, and recall of the black dots, how many do we have among the set retrieved. All right, so that's the concept of precision and recall. So in an ideal world, we would like to have 100% recall and 100% precision, at least in situation where the number of documents is not too large. But usually we have to balance precision and recall. So is it better to have 100% precision and 10% recall, which means that we're only going to see 10% of relevant document, but all of them will be good? Or is it better to have 80% precision and 20% recall? So essentially see more documents, but some of the documents that we're going to see will be irrelevant. there is no, no general answer to this question, but F measure is trying to balance precision and recall. All right, so this is the formula for so-called F measure or F1 score, and it says that to get the F measure, you multiply precision times recall and divide precision by precision plus recall. And you do 2 so that the final number is between 0 and 1. So let's see how it works. So in the perfect world, yes, we would have precision 1 and recall 1. Okay, so 1 times 1, 1 plus 1. So this would give us 1 divided by 2 multiplied by 2 gives us 1. So the perfect precision and recall is 1. If we get no good documents, or we get no documents at all, one of these things is 0, so then of course the whole expression is equal 0. So imprecise or irrelevant move this F measure close to 0. And the rest of it is essentially a balance. So as you increase precision and keep recall the same, you essentially increase the F measure. And if you can also increase recall and keep precision the same, it's also gonna improve your F measure. So that is, a way of putting together precision and recall, and then comparing the quality of a classifier based, on these two numbers. You get precision and recall, and if you wanna say this classifier is better than the other, the usual way of saying it is because the F measure of the second classifier is better than the F measure of the first classifier. So applications of naive Bayes, I mentioned that it can be used for spam detection. It also can be used for language identification. So, for that, we can either look at words, but more often is enough to look at letters. So essentially, taking a small collection of letters from a document is enough to identify which language it is. Is it Polish? Is it English? Is it Russian? Is it Spanish? And naive Bayes classification, the classifier can be built fast and is accurate enough that it works very well. All right, so let's look at classification in some real application. So we talked before that the economy is moving from anecdotal decision making to decision based on data, all right? And this process will open a number of text analytics applications, including text analytics in fraud detection, risk analysis, healthcare, and so on and so forth. So we're going to talk about fraud detection. This is a real example. All right, so let's look at it. So what we have here is the following, okay? We have a situation of a fraudulent transaction performed by organized criminals that was undetected by all financial institutions involved, and it is very easy to detect with simple text mining techniques. We have a merchant gateway as one of these institutions, which is a service that automates the payment transaction between the shopper and the merchant. There is a bank which issues the credit card. There is a merchant bank. There is a store online, and Visa, which sort of issues the cards and checks whether somebody is or is not creditworthy. So the example comes from the Analytic Bridge blog or group and is freely available online. All right, so here what we... Cześć, jak się masz?
Czego się dzisiaj nazywasz w ogóle?
No ja
jesteś?
przyszedłem i
Nie
miałem się odezwać po wykładzie.
Dobra. Będę jutro.
Będziesz jutro? No to dobrze.
Której zaczynasz? Jak się umówimy? Rano, po południu, po
O,
skończysz?
łatwiej jest mi się umówić po południu, jeśli
Czyli
będzie.
o której kończysz?
No kończę 2:15, czyli 2:30 moglibyśmy
Dobra,
się umówić.
jesteśmy umówieni.
No to dobrze.
Cieszę się, że Cię widzę.
No i nawzajem.
Zdrowiu
Tak,
i w pełni sił.
tak.
No dobra, to sorry for interruption.
No dobrze,
Do jutra.
dzięki.
Przepraszam bardzo.
All right, so what do we have here? All right, so we have a business-to-business merchant with very good rating located in the US. All right. Usually you can distinguish business to business from business to customer. All right. The purchase is taking place on a Friday night, and that is somewhat unusual. The cardholder address is somewhere in Chicago, Illinois. There is a phone number associated with the transaction, but it's listed in Grand Island, New York. But previously it was reported as an Indian cell phone number. All right. The product that's being purchased is a product with a higher fraud risk. And because the historical data shows that the risk associated with this product is higher than other products from the same merchant, all right? So that's what we see in the transaction, all right? What else do we know about this transaction? We know that we know the IP address of the transaction, and we know that it is this company that is associated with this IP address. There is a domain server in Dallas, Texas, and it's owned by a guy with this name who's located in India. In addition, the domain name contains the name proxy, which should be a red flag. All right? A Google search on the phone number points to a fraud report about Christian Kingdom Shipping Company and blah, 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 all right? And it's available at this URL. And the email address of the purchaser is this thing. And integrityholdings.com is a non-existent website, all right? So that means that the purchaser provided a fake email address. All right, so all of this suggests that, that this kind of fraud could be automatically detected. So you can capture the name of a number of metrics from the online purchase form, that is phone number, email address, all right? And they can be fake, but then they can be checked against real data by searching the email address and the domain attached to it, all right? And creating a feature such as, is the domain name empty? Is it a free mail account? Yes, what country it is? Can you successfully ping the email address? You can do a search on the phone number. Does the search return results containing some of these strings such as abuse, scam, spam, all right? So this is something that's amenable to automation, all right? So essentially the methodology to detect this kind of fraud is record IP address, do reverse lookup, to do the domain name also, and see if it's a non-corporate proxy. What is the country? All right, are these address, phone number, email address, and cardholder address all in different states or countries, all right? Once you have this data, you can then, the company, since it knows which transactions were later classified as fraudulent, it can create essentially a training and test data set and apply a classifier to any new transaction that's coming in. So here you have an example of using some simple text mining together with data coming from the web and classification to solve a real problem. So now notice that this is something that the pieces of which we covered in this lecture. Yes, classification was covered just a moment ago. All right, we were talking about classifying documents, but your features don't have to be words. Yes, you can classify the transaction, and in this case, your term document matrix could say, okay, if the country, is in Asia, say the feature would be 1. If it's the US, the feature could be 0. Yes, if the country is in Europe, the feature could be another feature could be 1. So you can have this collection of features which capture the relationship between different pieces of information that you enter when you try to perform online transaction. So this is one aspect of it. All right. The second aspect of this particular example has to do with the example that we've seen at the beginning. Namely, we looked at this log-like study of Yuri Lifshitz, where he connected articles published by various newspapers, such as New York Times, with their scores based on social network data. So here, instead of doing social network search, we can simply do a Google search and again connect these pieces of data, put it as a feature into the vector. Okay, is this phone number associated with the word scam? So essentially what you look at is you do a Google search on the phone number, you retrieve the first 10 documents, you look for the word scam there. If you find the word scam, you put a feature 1 in the scam column. All right. So instead of doing social network, we just do the Google thing. Before we were discussing creation of a dictionary. Yes? So we created a dictionary to build a Bayesian classifier for earnings. Here we are building a classifier based on different features about the properties of IP addresses, properties of domain names, and a feature could be 1 if the email address is associated with the word fraud, or if the email address is not a real company email address, but say a free email account on Google or Yahoo. All right, so that's so the moral of this is that the techniques that you learn for text mining are not only applicable to text mining. All right, that you can create real applications out of the pieces that we learned so far in the class. So to find a phone number and email address, you have to do tokenization, and you have to do a smart tokenization. You have to know that, say, a phone number in the United States should have, say, optionally a parenthesis at the beginning, yes, then 3 digits for the area code, close parenthesis, and then another 7 digits with possibly 2 spaces there. All right, so you have to take the whole string with some spaces in between and possibly brackets. You have to take it as one token, so you have to do some smart tokenization. Similarly, for email address, all right? Search on email address and the domain attached to it. So after you tokenize, yes, you have to do, you have to create some architecture. So you have to take the piece of text that you gotten from the form. You have to go to Google, yes, which requires some programming, you have to get documents, a URL from Google, then you have to capture these documents, do some simple scan of these documents and create features. So essentially you have to perform some very simple text mining based on a collection of features that you are interested in. All right? So, so we talked about architecture. I mean, for instance, the Watson architecture. We talked about the steps that are needed to create a Bayesian classifier or any classifier for the moment. So this has already covered the piece of this application. So what remains is to discuss search. How do we do search, and what are the techniques behind search, and then how do we get from a search result, which is usually a URL and a snippet of a document, to the full document. So some of it we're gonna cover next time. All right, so we already covered that. So to answer the question, reverse lookup of the IP address, we need to have some architecture for it, and the result of all of this processing is document feature matrix. And this credit transaction score is essentially the process of classification. So the homework for this activity would be draw a block diagram of these functions for this particular example, and see what it would take to implement it in practice. All right, so for the test, yes, you have to understand the concepts that are listed here, that is term document matrix, the steps that are required in classification, the estimations of priors and likelihood, so basically the estimation of probability of the word given label and probability of the document given label, and the formulas for classification, so the posterior, that is probability of the label given document. You have to understand the independence assumption, that is, we are modeling a document as a collection of words, and there is really no relationship between these words that is captured probabilistically. So that's the basis of the naive Bayes classification. All right, some questions that you may want to consider answering. All right, we can skip that right now. All right, so this we can incorporate in the next lecture. All right, so I want to talk about two more classifiers. One is the rule-based decision tree classification, and an example of such a rule-based classification was a mail routing for a large US bank. So the real project had to do with the following, that customers very often write to the bank by filling an online form, but the bank has internal processes. Okay, is the customer inquiring about a new mortgage or an old mortgage? Is the customer trying to possibly open an account or close an account? Okay, or they trying to pay off mortgage early and close the mortgage account? So there are several categories, and what we did with this particular bank was to create a classifier that would take the text of the online generated message and put it in the appropriate bucket, and then the system would forward this particular email to the clerk who could deal with the particular topic. So as it happened, a decision tree classifier seemed to work better, or maybe that's what the bank wanted, and that's what got implemented. Another example that we're going to cover is nearest neighbor classification, and there are some neat application of nearest neighbor classification that we're going to see in the video. All right, so rule-based classification. This is relatively simple. All right, so for instance, we have, okay, so this is a decision tree, and essentially we are checking a number of conditions, and depending on which conditions are satisfied, we put the document or a situation into two categories, X or Y. So X is a category, Y is a category, and we are answering some question. Is the feature A less than 2? If it's true, then check the feature B. If it's less than 2, then put it in bucket X. On the other hand, if A is less than 2 and B is less than 4, then put it in the bucket Y. All right, so this is the decision tree, because you check some conditions, and depending on these conditions, you make a decision about which class a document belongs to. All right, so what are the advantages? Well, it's human readable, because you can see, how you made these decisions. You can also edit it. Maybe you want to change here from B less than 4 to B less than 3, all right? Because B less than 4 doesn't make sense to it, all right? And people like this kind of representation because it gives them a sense of control. So let's look at it, all right, with some interpretation. So A could be number of previous transactions with this merchant using this credit card, all right? So did we have less than 2 transactions, so 1 or 0 before, or did we have more than two transactions, all right? So B could be the current transaction amount or median transaction amount. So is the current transaction amount less than $2,000, for instance? And X could be the decision, approve, and Y would be don't approve. All right? So the rule would say that if we had few transactions and a small amount, then you can approve. But if you have, or if you had a lot of transactions, also approve, yes? On the other hand, if you had few transactions and the amount is between 2,000 and 4,000, then don't approve. All right, so that's essentially what this decision says. Okay, don't approve if you have the amount between 2,000 and 4,000 and no prior record of transaction or small prior record of transaction. All right, so it sort of makes sense. I mean, this is of course an invented example, but this kind of decision tree would be used for approval of the real transactions. And actually, I mean, some of these features that we mentioned before are already used by credit card companies. So for instance, when I moved to Charlotte at the beginning of January and try to I can't remember what I tried to buy, but I think I tried to do a large purchase maybe of this computer and have it shipped to Charlotte. Then of course, the fact was that the shipping address was not the same as the billing address for the credit card, since I still have my billing address in New York. And the amount was sort of relatively large. So despite the fact that, I had quite a few transactions, with this particular merchant, they refused the transaction. So I had to call them and explain them that I now have two places where I live, which is New York and North Carolina. All right, so we don't have time for the demo, but the applications of predictive text mining book, fundamentals of predictive text mining book comes with another toolkit called RigText, all right, where you can do rule induction, so you essentially can create decision trees like that. And, I did the same experiment with, this time with about a few more elements in the vector space, but the dictionary size was actually quite similar. Created a decision tree and computed the statistics for a rule-based classifier, so a classifier that looked like a tree that you saw before. The results were better than for naive Bayes, okay, because the F measure was about 93% here. So, and again, I mean, the machine gives you the actual output so you can see how well you can do. So I actually looked at these rules, and some of the rules look like this, okay? November and estate. So if you have the word November and you have the word estate, then you can put it in the class earn. All right, so I thought, how about adding December and estate, yes? And maybe that would improve the classification. Then we had stuff like det and November to earn, okay? So I added a few of these manually, yes. There were quite a few examples like 2 words and a month, all right, the predicted earn. So you would have, I don't know, det and estate and November, then earn, det and estate and July, then earn, okay? So examples like that. So I thought, well, what's wrong with April? Okay, so I just delete, since there are quite a few examples of that form, for some of them I deleted the months, so made the rule more general. Just having the words should predict the category earn. It all made sense to me when I was doing the editing. However, the results were worse, all right? So in this case, the precision dropped substantially. The recall actually increased, but the total performance as measured by F measure dropped, all right? So if we care more about the recall, well, this kind of generalization made sense, but unfortunately, it also gets, 4% more garbage than it did before. So there is, there is a 4% drop in precision associated with this manual rule editing. So I think that the moral of the story is that in general, it's difficult for a human to beat machine in creation of classification rules. When the combination of human and machine performs best is when human choose the features which are relevant, okay, that is either words that are relevant or situations that we care about, for example, okay, is this phone number associated with the word scam, yes? That would be a feature, and this is a judgment that the machine will not have independently. So humans can create these kind of features, but then the actual computation of the best combination of parameters or or specific rules is better left to the machine. So here you see the combination of the naive Bayes classifier with rule-based classifier. So on a similar dictionary, there is about 6% difference in F measure, but the naive Bayes classifier has a higher precision. It's just that the recall is much lower than the one of the rule-based classifier. So depending on what we want, we can play with these numbers. All right, so the final classification topic of today is k-nearest neighbor classifier. So the idea here is the following, that we have a new document, which is here in green, and we have categories, which is blue and red. And the question is, what do we do with this new document? Shall we change the color to blue, or shall we change the color to red? All right? So the idea is that instead of doing something like Bayesian or rule-based classification, we somehow see how close it is this new document to the documents that we already labeled, and just choose the label of the two closest ones. So this is 2 nearest neighbor classification. It could be a 3 nearest neighbor classification. All right, so we can say that we're gonna choose sort of 3 closest documents and then take the majority vote. So 2 nearest neighbor would be here, 3 nearest neighbor would be here, 5 nearest neighbor would be looking at this circle, and then we have 3 blue. So depending how, what classification method we use, I mean whether we use 2 or 3 or 4 or 5, we may have different results. So again, what is the right K for K nearest neighbor classification is an empirical question. There is no general answer, but one can experiment with different Ks and see which ones perform best. Here you have an example of a 5 nearest neighbor classification from Taming Text. And Taming Text has a very nice exposition of classification. So if you get the book, please read this particular chapter. All right, so this is the idea. The idea is very simple. You have a new document which look at which documents are most similar to it, or how close it is to other documents. Look at the labels of these documents and take the majority. So what remains to be discussed is how do we decide what is near, okay? How do we measure the distance? And there are different distance matrix. So here are the two. So the first one is the Manhattan metric, which measures sort of the difference coordinate-wise, all right, and simply adds it. So this is like you go on a city block, and if you want to go from point A to B, you just count the number of city blocks that you traverse, and this is the regular Euclidean metric, where d is the square root of this difference. All right, so these are the commonly used distances. Obviously, this one would be somewhat faster to compute, but there isn't that much difference. We will introduce a cosine distance tomorrow, I believe, as the third very popular metric. Instead of measuring distance, we can measure similarity directly. So, for instance, if we have these documents, okay, so we have term document matrix here, and these are the categories, all right, of the document. Then we can measure in how many places this new document corresponds to, to the document in class 1 versus class 0. All right, so 1011 matches these two guys in two places, so the score is 2. And then say for this guy the score is 1, and so on and so forth. So we get essentially similarity scores for different classes, and then the majority, the closest similarity measure would give us, the most similar documents. So similarity score. So this would be the document. These two would be the closest documents, highest similarity score, and both are in class 1. So this document would get the assignment of class 1. So that would be a different way of assigning a class. A variation on the theme, instead of measuring the similarity to all documents, you just measure the similarity to the centroid of the documents. All right, so we have, in this example, we have 3 classes, which the documents are about United Kingdom, Kenya, and China. Since the documents are represented as vectors, say if we have 20 vectors in each class, we can take the average of these vectors, and then when we have the new document, we just measure the distance between the vector of the new document and the particular averages, and that's how we do the classification. So this is called a centroid, or sometimes the Rocchio classifier. So that's a different name for it. So it's a variation on the theme. This could be a homework, but maybe we can actually watch it now, since I have a connection to the network here. So let's just see. But we don't have the voice.
The k-nearest neighbor classifier is one of the most straightforward classifiers in machine learning. A new example receives the class of its nearest neighbor, or k-nearest neighbors, in memory. When k is set to 1, each memorized example implicitly occupies a multi-edged cell in which it is the nearest example around. Together, all examples in memory form a class space with multi-edged boundaries between the classes. This is quite different from the class boundaries that the decision tree learner distinguishes. In the separate learning phase, the decision tree learner draws a minimal number of axis or orthogonal lines to divide the class space. Here is one example of the usage of k-nearest neighbors in a real-world task, the pronunciation of words, which is needed to produce synthetic speech, like the voice you are hearing. When trained on the dictionary of word pronunciations, a k-nearest neighbor classifier is capable of 2 things. First, it will always remember each pronunciation it has stored in memory. Second, it can pronounce unseen words by analogy with the memorized examples. For optimal generalization, it is best to store examples of letter pronunciation in context instead of full word pronunciations. Here is an example of the pronunciation of the 6-letter word faces as it appears in the dictionary. First, we align the 6 letters to the 5 phonemes. This can be done automatically. We then encode the word stressed as another layer of information. We can now create examples to be stored in memory. A first example is the letter T, preceded by no other letter and followed by the letters H, E, and S. In this context, the letter T is pronounced as the. The second example is the letter H, which aligns with the code stating that it is not pronounced. It is jointly pronounced with T. The same procedure would generate examples for all letters. We do that for all the words in our dictionary, filling the memory with hundreds of thousands of examples. With the k-nearest neighbor classifier, learning means memorizing examples. Next, here is an example of how classification works. Suppose that we are interested in the pronunciation of the letter A in the word hearts. The classifier has memorized the pronunciation of similar words like theirs, clears, heard, but also hard, hardy, and hardly. The classifier works for the k-nearest neighbors around the new example. Upon finding the nearest neighbors, it counts their majority class. In this case, they unanimously predict one pronunciation. Displaying all letters are pronouns, and their pronunciations are concatenated to form a complete word pronunciation. This approach to word pronunciation is actually hardly surpassed by any other method. It is a typical example of the simplicity and the strength of the k-nearest neighbor classifier.
Okay, so as you can see that, this is a very neat example of k-nearest neighbor classification. There is some other stuff, so if you feel like it, you can watch it and read about it. One question that you may want to ask yourself is, what takes more computation, a nearest neighbor classifier or a naive Bayes classifier? And when does this computation take place? So I think this is it for the lecture. So let's discuss some other stuff. All right, namely homework. All right, so let's see what you should be doing, and let's discuss what it is that might appear on the exam. So definitely you can expect on the exam, and I would urge you to do this particular homework, that is, redo the Bayes theorem example that we had in the class, and put some other numbers there, like the ones suggested in this homework, and see that you can redo this example without looking up the Bayes formula. That is, do it completely from memory, and then re-examine your example using sort of 1,000 people population and see if it still makes sense. You can expect on the test something along the line, okay, here's a description of a problem, sketch an architecture that would solve this problem using techniques that you learned in class. I mean, that is a very typical assignment that I give on an exam. What this problem could be? Well, it could be something along the line of, a credit card fraud detection, or finding negative opinions, or classifying something as positive or negative. I'm not sure exactly what it's going to be, but it's very likely that to understand the architecture, you have to understand what is the input, what is the expected output, what are the steps, and what are the boxes that would be associated with the steps. It doesn't have to be complicated, but you have to be able to do it. So one way to train for it would be to look at this log life study of Lifshitz that we discussed earlier in the class today, and see what the input output behavior are, and what would be the boxes and how they would be connected. Obviously, this is not something that you're gonna do today, but if you want to understand what's how to do language processing, you should at least go through 2 chapters of the NLTK book, Experiment with Python, see what it is that what are the basic operations of counting words, creating n-grams, plotting the distributions. We had a very simple demo, and it's really not more complicated than that. It's just the question of installing the tool and then going through the examples. I think it's going to take you more time to install than go through one of the chapters, because it's really elementary, and installation usually takes some time. We discussed parsing today. So can you take these representations that you see here in the brackets and create a parse tree? So decide what is a noun, what is a verb, where is the noun phrase, where is the verb phrase. Can you draw it? If you want to know more about parse trees and parse representation, check the link grammar. Read something about k-nearest neighbor classification. You can expect a question of the form, all right, here are the points, here's a collection of points, here's a new point, do a 3 near neighbor classification of the new point. Will it be class A or class B? And that would be a very natural question on the exam. Again, architecture question. So this is the homework. In addition, on the exam, you can be almost sure that there will be something related to the naive Bayes classification. So if you have any questions about it, I mean, maybe now would be the question to ask. Otherwise, the material will be available there. So, I mean, look at these collection of words, collection of documents, the estimations of probabilities, and see if you can do some of these examples on your own. I think that would be it. So these are the topics that possibly might appear on the exam. So thank you very much. I appreciate being here, and if you have any questions, I would be happy to answer them now. Otherwise, I'm pretty sure you are tired, so we're gonna meet again tomorrow. Thank you.